Let's look at some examples using the Buckingham Pi theorem and dimensional analysis. We're given that the wave speed c is related to water density ρ, gravity g, wavelength lambda, mean depth of water h, and wave height small h. Hypothesize an equation that relates c to all other variables and identify the dimensionless groups. So what we want to do first is to identify the dimensions of the variables. So c is the wave speed. It should have meters per second, which is length multiplied by time to the inverse. Density should have kilograms per meter squared, so it's mass per length to the cube. Gravity is an acceleration, so that should give us length per time squared, so -2. Wavelength is a length, so that gives us dimension of L. Depth of water, also a length, and wave height, also a length. Now we can use the Buckingham Pi theorem to determine how many dimensionless groups we can get. First, we want to identify the number of quantities. Here we have in total 6 quantities: c, ρ, g, lambda, big H, and small h. Then we want to determine m, the number of independent dimensions. Note that the number of independent dimensions is not necessarily the same as the number of base dimensions. So to determine the number of independent dimensions, we can select, for example, lambda as 1, that's representing the length. We note that ρ is the only one that has the mass, so that we can also select as an independent dimension. And we can select either one of c or g because they have time as a dimension. I can select, say, c. So there are in total 3 independent dimensions. G is not independent of c, ρ, and lambda because it contains L and T, which can be rewritten by c and lambda. And H, big H, and small h can be is dependent to lambda, so they are not independent from each other. So the Buckingham Pi theorem tells us that n minus m is equal to 3, so we should have 3 dimensionless groups. Now, to identify the dimensionless groups, we need to invoke dimensional homogeneity. So this tells us that c could be equal to or proportional to ρ, g, lambda, big H, and small h, each raised to some power, say a, b, c, d, e. And now I can substitute all the dimensions into this equation. So I have L to the t minus 1 is proportional to ml3 raised to power of a, lt minus 2 raised to power of b, and L raised to power of c, L to the d, and L to the e. Now I can group these by variables, because each of these variables, L, T, and M, their exponents is same on left hand side and the right hand side. And so this gives that on the left hand side I have 1 is equal to 3a minus plus b plus c plus d and plus e. For time t, I have minus 1. On the right hand side, I have minus 2b. Finally, For m, on the left hand side I have no m, which is 0. And on the right hand side I have a. So I can solve for this. B is equal to 1 over 2. And for the first equation, I can say solve for C. A is 0 and B is 1/2. Move the 1/2 to the left. 1 minus 1/2 is still 1/2. And move D and E to the left, so minus D minus E. So now I can substitute all these back into the original equation. Substitute all these back to the original equation. I can get that C could be proportional to, so A is already 0, so rho does not come into this equation. This makes sense on dimensionality grounds because if you have a mass on the right hand side, you must have a mass on the left hand side, but you don't. So rho shouldn't be there. So G raised to the power of B, and B is 1/2. Lambda raised to the power of C, which is 1/2 minus D minus E. H raised to the power of D, and small h to the power of E. And now we can group by the exponent. So either it's the constants, exponents, or exponent of D or exponent of E. So on the right hand side, group the constants. So we have G to the 1/2, lambda to the 1/2. And anything raised to the power of D is lambda minus 1 and H raised to the power of D. Anything that's raised to the power of E is lambda minus 1 and H. And I can move the constants to the left. And this gives us CG minus 1/2. Lambda minus 1/2 is proportional to lambda minus 1 H raised to the power of D and lambda minus 1 H to the E. If this still looks unfamiliar to you, you can also rewrite it in terms of fractions. So C divided by square root of G lambda is proportional to H divided by lambda raised to the power of D, and small h divided by lambda raised to the power of E. Note that you can also invert the numerator and the denominator, and that's still fine because we haven't determined the exponents D and E. They could be positive or negative, so that flips the numerator and denominator. So here we have the equation that relates C to all other variables. And the dimensionless groups we already solved, which are C divided by, so these are C divided by square root of G lambda raised to some arbitrary power, let's say A, and H divided by lambda raised to the power of B, and small h divided by lambda raised to the power of C. Here you can immediately see the power of dimensional analysis. First, it rules out the need for rho on just purely on dimensional grounds. We didn't even look at the physical meaning. And second, what dimensional analysis allows us to do is to reduce the number of experiments. Imagine that now you have 5 variables, so C, rho, so no rho, C, G, lambda, big H, and small h. You could try to vary all 5 variables. Say you have 2 numbers per variable, then you need to do 2 to the 5th combination of experiments. However, now you can use these non-dimensional numbers. What you can do is to, on the x-axis, have C divided by square root of G lambda. On the y-axis, you can have big H divided by lambda. and say you do some experiments and find out at different h divided by lambda, what are the trends. So now what you need to design is to design based on these dimensionless groups. So you reduce the number from 2 to the 5th to 2 to the 3rd, which saves a lot of time and money. Well, it might seem very tedious to solve all these systems of equations just to arrive at a dimensional argument. What I like better is actually solving these problems by using stand-in variables. It's like solving a puzzle. How it goes is that you first want to choose stand-in variables. You start from the simplest dimensions, for example, base dimensions, if there is any. In our case, the base dimensions, we see all these 6 variables. The most basic one is L. I can choose any one of them. Say, let's choose lambda. And after I choose lambda, I want to choose variables that cover other base dimensions. So for example, I must choose rho because it covers the base dimension of mass. And from C and G, it really doesn't matter which one I choose. I can choose the one that has the least exponents, but it must contain t. So let's say we choose C. So after the simplest dimensions, choose variables that cover all base dimensions. So here we chose C, rho, and G as the stand-in variables. Now what we want to do is actually transforming this problem to a problem that lets us prove that the other variables that we didn't choose, so G, big H, and small h, are not independent of the variables that we have chosen, which are C, rho, and lambda. So this is actually a proof to the Buckingham's Pi theorem, saying that the other variables, other than the stand-in variables, they are not independent of each other. So let's start with the easier one, say h. H has a dimension of L, so what I want to do is to make the L disappear using the stand-in variables. So here, the stand-in variable for L is lambda. So what I want is to piece a L minus 1 such that the L minus 1 and 1 cancels out, right? So what I need is actually a lambda minus 1 here. So that gives us the first non-dimensional group, h divided by lambda raised to some arbitrary power. And the same goes with little h. So little h has a dimension of L to the first power. What I want to do is to make the L to the first power disappear, so I want to multiply by L to the minus 1. And what's the stand-in variable for L? That's lambda. So I have lambda minus 1. So that gives us the second dimensionless group. And just a reminder that we have lambda is the stand-in variable for L, C is the stand-in variable for T, and rho is the stand-in variable for M. And now let's look at the harder one, G. G has a dimension of L, T minus 2. So we have 2 variables here. So which one should we choose to make it disappear first? Let's imagine if we choose L first, and I make the stand-in variable for L come in, then I need to deal with T. But the stand-in variable of T, which is C, the wave speed, also contains L. So if I do that, then I need to deal with L again. So I don't want to do it twice. So what I want to do is to use the stand-in variable of T. first because it contains L. Okay, so what I want to do is to make t disappear, so I want the standing variable of t, so L t minus 1. What I want to do is to have t minus 2 multiplied by t to the 2. So what I want to raise this to the power of is raised to the power of minus 2. So minus 1 and minus 2 gives me 2. And this gives us c raised to the power of minus 2, because this is the dimension of c. Okay, so these cancels out. So now I can deal with L. Here I have L raised to the power of 1 and L raised to the power of minus 2. So this is in total L raised to the power of minus 1. In order to make this minus 1 disappear, I want to multiply by the base, the standing variable of L, which is lambda, raised to the power of 1, so such that the negative 1 and 1 cancels out. So now I should have lambda raised to the power of 1. So this gives us that the dimensionless group should be g lambda divided by c squared raised to some arbitrary power, let's say b. And this should give us the same result as before, where we have seen that previously the result was c divided by g lambda raised to the arbitrary power, say d. So these are interchangeable by just changing the exponents. So indeed, we got the correct non-dimensional groups. You can already see that this method is much more fun and easy compared to the method we used previously, which requires solving systems of equations and algebraic manipulation. And here is just a puzzle.